In the last video, we looked at how we can take a logic circuit and generate a state diagram, and then implement a finite state machine as a representation. But now we want to look at how we can make a logic circuit from a state diagram. So on the left here, we have our state diagram, where we have state 0, 0, 0, 1, 1, 0, and 1, 1. And we have arrows which dictate jumping to the next state. And we also have this notation where we have the input, and then slash, and then the output. Now in this case, our states are represented by Q1 and Q2, and this input is going to be X, and the output is going to be Z. So we can simply look at all of our states here. So Q1 and Q2 are going to represent the states. So going down the truth table, we would have Q1 and Q2 equal to 0, which would represent this state here. So in the state 0, 0, when X is a 0, it's denoted up here, Z is a 0, and we jump back to state 0, 0. So we can fill in these entries as follows. And then if we're in state 0, 0, we jump to state 1, 0 if X is equal to 1, and then Z will be equal to 0. So following this convention, we arrive at this filled out truth table. And if there's any confusion on this, jump back to the previous video where we introduced finite state machines. So now that we have our truth table filled out, the next thing that we want to actually do is introduce some K-maps. So we're going to introduce K-maps for Z, Q1 new, and Q2 new. Now if we look at Z, we can see that we have a 1 when Q1 and Q2 are equal to 1, and then whenever X is equal to 0 or 1. So going to our K-map where we have X here and Q1 and Q2 there, we arrive at the following values. So we can fill out the other K-maps to have following tables. What we can do is then have our groupings. So if we look at Z, we simply get that Z is equal to Q1 times Q2, or Q1 new, we get a Q1 new is equal to Q1 bar, Q2 bar, plus X, Q1. And for Q2 new, we get that that is going to be equal to this grouping of these four, plus these two, which is equal to X bar plus Q1 times Q2 bar. So with these functions, what we want to do is implement them into a logic circuit. And we can choose JK flip-flops or D flip-flops. Let's choose D flip-flops. So we just brought down our function Z, Q1 new, and Q2 new, and we brought down our original truth table for the D flip-flop, where we really are only going to be concerned with when the clock is high. And what we notice is that when the clock is high, on that rising edge, that Q new is essentially equal to D. So we know that our output function is Q1 times Q2. So we can have a logic gate here, and we can tie Q1 to that, and Q2. Now we're going to leave out the clock pin for this example for simplicity. So notice again that D is equal to Q when the clock is high. So what we can do is take D1 and set that equal to Q1 new, and D2 equal to Q2 new. If we look at D1, which is this input here, we're going to have an OR gate, and on that OR gate, we're going to have two AND gates. Now if we look at these AND gates, the first term is going to be Q1 bar, Q2 bar, which we can have an inverter after the Q1 signal, or we can use the Q1 bar pin, similarly for Q2 and Q2 bar. So this gate, the inputs will look like this, and for this other AND gate, we simply have Q1 and X. Now if we look at D2, again, we have an OR gate. It's going to be the input to D2. And from that OR gate, we're going to have an AND gate, which will consist of Q1 and Q2 bar. And then the other input to that OR gate is X naught. So we can have an inverter and tie this to X. So this circuit does look kind of messy, but it does represent that exact state diagram from the finite state machine. And like stated previous, this is the last topic that we're covering in the logic course. The next course is going to be advanced circuit analysis. Thank you for watching.